Hello everyone, my name is Geis and I'm a research assistant at the Communication Networks Institute of the TinyDRaGon University. And my presentation is about a novel signal strength prediction method that combines expert knowledge from the mobile communications domain with lightweight machine learning methods to achieve accurate and computationally efficient predictions. My talk is structured as follows. Firstly, I'm going to motivate our work in the context of lightweight radio channel estimation for 6G pervasive intelligence. Then we're taking a look at how to reduce DRAGON's model complexity. Following, I'm going to present the proposed TinyDRaGon model. Then we're taking a look at some results to evaluate and validate TinyDRaGon's performance. And finally, I'm going to conclude my talk and give an outlook about future research. In future, 6G networks connected and autonomous vehicles can massively benefit from predictive networking concepts, such as data rate prediction as well as signal strength estimation along future trajectories. For the latter, we need precise channel models. In our previous work, DRAGON showed the potential of machine learning-based channel models in this context, but its high model complexity lacks embedded system application. And therefore, we need lightweight machine learning-based channel predictions for small embedded platforms with power and computationally constraints. And for that use case, we present TinyDRaGon as a novel signal strength method. We presented DRAGON as a novel method for signal strength estimation using expert knowledge from the mobile communications domain, as well as a deep learning-based data analysis method with detailed geo information as inputs. So therefore we used two image inputs, the so-called side view and top view images, as well as an extensive feature vector. So all of these samples were then fed into a deep neural network. So this was a complex deep learning pipeline due to the image inputs. And in this paper we present TinyDRaGon, which is a novel variant of DRAGON that builds upon a more lightweight machine learning process. So in this case, we eliminate the image inputs so that this results in a reduced model complexity and that we can use more lightweight machine learning process. So this slide gives an overview about the proposed TinyDRaGon model's architecture, which I will present you in more detail in the following. So I will start with the input data. Then we have building information as well as terrain information. And based on this, we can later build a 3D model of our environment. And in addition, we have information about base stations in our scenario, as well as measurements that we will need later for training our machine learning model. So in this context, we use multiple LTE measurement data sets. The first one aggregates drive test measurements collected in the city of Dortmund in different scenarios. Then we have a second one that contains UAV measurements from the city of Aarhus in Denmark that were collected in different flight heights. Then we have more drive test measurements from the city of Copenhagen. And as a last data set, we have drive test measurements collected in the city of Wietfeld. So in total, these are nearly 400 data samples. As not all channel parameters are covered in our measurement data, we are performing a so-called IEEE fitting, where we fit our measurement data to a simple channel model to retrieve an estimation of the transmitting power. In addition, we are building a 3D environment of our scenario in Limousin by using the building information and the terrain information. And Limousin can then be used to extract the image samples. And based on this pre-processing, we can then perform our feature extraction. As mentioned before, we want to eliminate our image inputs and therefore we're performing so-called splits. So our top view sample is split into 5 horizontal areas by performing 4 horizontal splits. And then for each split, we extract the relation of building pixels. For our side view samples, we perform vertical as well as horizontal splits and then extract for each split the relation of building pixels as well as the relation of terrain pixels. In addition, we will include our position features like position of transmitting and receiving station, features extracted from the direct path like the number of intersections with building and terrains as well as the distance of the direct paths traveling indoor as well as through the terrain. And the channel defining features like the bandwidth, the frequency, the fitted epsilon value based on our IEEE fitting, and estimated pathways based on a simple channel model as well as the transmitting power. And so our overall feature vector is then holding 34 features. The extracted features can then be fed into a simple channel model in order to retrieve an estimation of our pathways L. And in addition, we use these extracted features for training a random forest model, which outputs a correction of the calculated pathways. And when we sum this up, we retrieve our received signal strength. This TinyDRaGon architecture can also be used to examine completely unknown scenarios in order to calculate radio environmental maps, for example. Now we want to evaluate TinyDRaGon's performance and therefore compare it to different pathways models. These include the conventional channel models such as Fry's Nakagami two-way ground, two empirical channel models, environment-aware channel models like obstacle shadowing, as well as the Altair WinProp ray tracing software, and the machine learning-based channel modeling with Dragon. And by taking a look at the plot, it can be seen that it is separated into three categories established by the single model's performance. So the first category, which is the one yielding the best results, hold the two machine learning-based prediction models. And even though TinyDRaGon is a comparatively simple machine learning model, it is capable to get even better prediction results than its deep learning predecessor. The second category consists of the empirical methods as well as the ray tracer, and the third and last category is the one performing worst, including the price-based models. And these models achieve a significantly lower prediction accuracy. Since TinyDRaGon performs better than the Dragon model, we also examined other simple machine learning methods. This includes a regression tree, a support vector machine, and a simple artificial neural network. And all the examined regressors outperformed the empirical reference model. The evaluation revealed that the formally investigated random forest yielded the best results here, while other simple regressors achieved worse prediction accuracy than the Dragon model. In order to analyze TinyDRaGon's generalizability over different scenarios, we are comparing multiple data aggregation approaches here. So firstly, this is a scenario-wise approach where an individual split evaluation is done for each scenario. Then we have the global approach where the model is trained using 80% of the aggregated data set so that the remaining 20% are then used for this evaluation. And the cross-scenario approach where for each subset, the model is trained in the remaining aggregated data, where the subset under investigation is used as the test set for the evaluation. And it can be seen that the scenario-wise as well as the global data aggregation methods achieve a very similar behavior with zero mean for all evaluation scenarios. And that the most challenging method here is the cross-scenario evaluation, as it reveals a structural difference between the training data sets, which can be seen in the worst prediction accuracy in the ARHUS data, as this dataset exclusively contains the AV measurements, which were not covered in the training data. Interesting in this point is the comparison with the Dragon model, because Dragon was most accurate when trained as locally as possible, while the TinyDRaGon model is better when trained globally. And TinyDRaGon is also significantly better for drive test data in the cross-scenario approach and is better than the empirical models, which was not always the case for the Dragon model. We also want to evaluate TinyDRaGon's computational efficiency. So first we're taking a look on the training time of the aggregated dataset of the machine learning-based models. Here it can be seen that training TinyDRaGon is roughly 10 times faster than training the Dragon model. Also, Dragon's training is GPU accelerated, and the TinyDRaGon training is done on the CPU and performed without parallelization. For the test case, we performed a test scenario in the Dortmund urban scenario that holds roughly 9,000 receiver positions and is then examined for one transmitter configuration. So for the environment-aware model, this encloses downloading and pre-processing the environmental data as well as the sample generation needed for the machine learning models. And here it can be seen that TinyDRaGon and Dragon require nearly the same amount of time of about 43 seconds and that the ray tracer takes 2.5 times as long. So in order to conclude, we presented a novel lightweight machine learning-based pathways prediction method called TinyDRaGon, which outperforms its deep learning predecessor Dragon and comes up with multiple advantages like that it allows faster training and an interpretable decision-making process. In future work, we want to apply TinyDRaGon in embedded systems, increase its generalizability, and utilize it in the context of machine learning-enabled network planning. Thank you for your attention.